Hi everybody, in this video we're going to look at composite functions with inverse trig functions. We really are looking at sine, cosine, and tangent still, and we want to find exact values. We don't really want to grab our calculator. So let's go back and talk about inverse functions a little bit. Hopefully you remember that when you find f composite f inverse of x, you get x, and when you find f inverse composite f of x, you get x. There's a little twist we have to do when we look at inverse functions, and primarily that has to do with domain. When we look at the sign of sine inverse of x, we get x, but x needs to be greater than or equal to -1 and less than or equal to 1. Cosine of cosine inverse of x is also equal to x, and x is again greater than or equal to -1 and less than or equal to 1. Tan of tan inverse of x is equal to x, but this time x is from -infinity to infinity, so notice there is a difference between sine, cosine, and tangent. What I want you to think about is our answers are ratios. When we're applying the inverse function, we're taking the inverse of a ratio. This inverse of a ratio gives us an angle. Then if we apply sine, cosine, or tangent to that angle, we come back to a ratio again. So this is a ratio in and a ratio out. I want you to see the difference when we change the order of the functions. If I have sine inverse of sine of x equals x, now x is an angle, so x will be greater than or equal to -pi/2 and less than or equal to pi/2. Cosine inverse of cosine of x is also equal to x, but for cosine, x is greater than or equal to 0 and less than or equal to pi. Then tan inverse of tan x is x, and x is greater than or equal to -pi/2 and less than or equal to pi/2. Think about where we're starting. We're starting with taking the sine, cosine, or tangent of an angle. When we do that, we get a ratio, we apply the inverse function of the ratio, and we come back to an angle. So this direction of composition will always give us an angle as an answer. So let's do some practice. We're going to find exact values of each composite function. I'm going to start with sine inverse of sine of pi/9. What I want you to think about is the angle we're starting with, pi/9. Because it's between -pi/2 and pi/2, our answer is simply just pi/9. Our next problem says sine inverse of sine of 5pi/3. 5pi/3 is not between -pi/2 and pi/2. So let's look at our unit circle and think about what we can do. 5pi/3 is equivalent to -pi/3, so the sine of 5pi/3 will be equal to the sine of -pi/3. This, as our solution, is -pi/3. Let's try that with cosine. The first one says cosine inverse of cosine of 3pi/4. When I look at cosine, my angle can be from 0 to pi. 3pi/4 falls within those numbers, which tells me that the cosine inverse of cosine of 3pi/4 is just 3pi/4. Our next one says cosine inverse of cosine of -pi/6. -pi/6 is not between 0 and pi, but cosine is an even function. That means that cosine of -pi/6 is the same as cosine of pi/6. If I take the cosine inverse of cosine of pi/6, I'll get pi/6. Remember, tangent goes from -pi/2 to +pi/2. I'm starting with the tangent of 2pi/7. This is good news. Because 2pi/7 is between -pi/2 and +pi/2, my answer is just 2pi/7. But when I look at the tan inverse of tangent of 4pi/3, I can see that 4pi/3 doesn't fall between -pi/2 and +pi/2. So let's bring back our unit circle. 4pi/3 is in the third quadrant. Tangent is positive in the third quadrant. This means I need to find an equivalent angle where tangent is also positive. That means we can use pi/3. If I take the tan inverse of tangent of pi/3, I'm going to get pi/3. It's important that we talk about notation for inverse functions. There are two common ways to write inverse functions. We've been using -1, but you'll also often see arc functions. So sine inverse of x can also be arcsine of x, cosine inverse of x can also be arccosine of x, and tan inverse of x can also be arctan of x. Let's find the exact value of cosine of arcsine of √2/2. For our composition, we start with the arcsine of √2/2. This is going to give us an angle. The arcsine of √2/2 is going to be pi/4. So we need to find the cosine of pi/4. Sine and cosine are the same at pi over 4, and they are both the square root of 2 over 2. The next one says find the sine of the arcsine of 1/2. Again, we're going to start inside with the arccosine of 1/2. Arccosine of 1/2 is pi over 3. Then when I find the sine of pi over 3, I get the square root of 3 over 2. Notice that my answers are exact. I am leaving my radicals and I am not changing to decimals. Next we have tangent of cosine inverse of the square root of 3 over 2. So I'm going to start with cosine inverse of square root of 3 over 2, which is pi over 6. Looking at the tangent of pi over 6, we get that it's the square root of 3 over 3. I think this is a good practice for using our unit circle. If you have to look back at your values, it's okay, but it's really important to know these common ratios. Next, I have cosine inverse of sine of 5 pi over 4. I thought it would help to look at our unit circle. 5 pi over 4 is in the third quadrant. In the third quadrant, sine is negative. With pi over 4, you should associate it with the square root of 2 over 2, so I know that the sine of 5 pi over 4 is negative the square root of 2 over 2. So we're looking for the cosine inverse of negative the square root of 2 over 2. We can only find the cosine inverse from 0 to pi. When I think about the ratio of the square root of 2 over 2, it always happens at a multiple of pi over 4. Looking at the quadrants where cosine is negative, I know I should be looking in quadrant 2. My multiple of pi over 4 is 3 pi over 4, which is our solution. Let's look at cosine inverse of tangent of negative pi over 4. Again, I'm pulling up my unit circle. Negative pi over 4 is in the fourth quadrant. In the fourth quadrant, tangent is negative, and the value of tangent of negative pi over 4 would be negative 1. Now we need to find the cosine inverse of negative 1. We can't use negative pi over 4 because it doesn't fall between 0 and pi. So again, we're back to quadrant 2, where cosine is negative, and we know cosine is equal to negative 1 at the value of pi. Our last problem says find the cosecant of tan inverse of 5 over 8. 5 over 8 is not a normal ratio that we see with a unit circle. To help us solve, let's draw a triangle. The opposite will be 5, the adjacent will be 8, and let's call the angle we're looking for theta. Tan inverse of 5 over 8 is going to be equal to theta. This says we're looking for the cosecant of theta. Cosecant is 1 over sine. Sine is opposite over hypotenuse. So the next thing we need to do is find the value of the hypotenuse. This says we need to use the Pythagorean theorem. The Pythagorean theorem says 5 squared plus 8 squared will be c squared. 5 squared is 25, 8 squared is 64, that's equal to c squared. When I add 25 and 64, I get 89. That says c is equal to the square root of 89. Now that we have that on the triangle, we can find the value of sine. Sine of theta will be the opposite 5 over the square root of 89. If we take the reciprocal of that, we get cosecant. This says cosecant of theta is the square root of 89 over 5.